So this is quite an easy talk for me in some sense because it's all about galaxies and 1 gigayear at a time. So at Nottingham University, the whole astronomy department, they research on galaxies. So that's all we do. So I hear a lot of talks on galaxies and we all do lots of research on them. So it's like coming home. So I'm hoping to bring to you some of the reasons we study galaxies. And the 1 gigayear, so a gigayear, if you haven't come across it, is 1 billion years, 1 with 9 zeros after it. And that's about the time anything interesting happens to a galaxy. They're very slow moving things. And actually this whole thing is spelt out in Galaxies. So it says across here, Galaxies and Julian Onions. That's all written using galaxies that have been found by people over the years. Right, so just in case anyone was got the wrong end of the stick, we're not going to be talking about chocolate as such, or indeed the latest in mobile phones, which seem to be getting ever bigger. Now, we will be talking about things that happened a long time ago in galaxies far, far away, but not necessarily the franchise that provoked these sorts of things. So anyway, if everybody is all okay with that, we'll start looking at some galaxies. So these are galaxies. These are all very nearby galaxies. You may well recognize some of them. And this is the kind of thing we don't actually study at Nottingham, really, because they're all far too close and people know far too much about them. So we look at much more distant ones typically, or at least most people do. But anyway, there's lots and lots of galaxies. In fact, one of my ex-colleagues calculated that there are about 2 trillion galaxies in the visible universe. So there's plenty to study in that 2 trillion. And the other thing is there are galaxies all the way right to the edge of the universe. This is one of the deepest images ever taken, the Hubble Ultra Deep Field image taken over, I think, about 11-day exposure. So that's quite some tracking. And everything in there pretty much is a galaxy, except for a couple of stars with the diffraction spikes. This is a slide that works really well in person, but not quite so well virtually, but I don't know, you may have a smile at that. But to sort of base you in, or give you the basic units, you probably know some of these, but this is units of measurement. So the smallest unit of measurement really used by astronomers is the astronomical unit, which is the distance between the Earth and the Sun, and now fixed at around 93 million miles. So that's 1 astronomical unit. It's very useful for working with planetary astronomy because most of the planets around the Sun are in units of that. You know, Saturn is 10 astronomical units and Uranus is 20s, so on, so that they're not too difficult to remember. But we don't really ever use that when we're talking about galaxies. It's just far too small and not really useful. The next thing up is the light year, or the parsec. Most professional astronomers tend to use parsecs. I don't really know why. I think light years are a much more intuitive measurement, but anyway, that's what we have to go with because that's what we're stuck with. So a parsec is roughly, very roughly, about the distance between stars. In some places in the galaxy or in the universe, stars are a bit closer than that. In some places they're further apart, but you don't go far wrong if you equate 1 parsec very roughly to how far you'd have to go to the next star. And this is a phenomenally large distance. So if we took the Sun, which is a very large body, and shrunk it down to about the size of a marble, so about ½ an inch or a centimetre across, and in my case plonked it down in the centre of Nottingham, the nearest star, being a parsec away, would actually be somewhere on this ring here. So you can see you travel from Nottingham here holding a marble, and you have to travel to sort of the middle of the English Channel to come across the next marble. So they're very, very far apart, and you know, most of the galaxy is really empty space. So having said galaxies. What is a galaxy? And this is what we see as a galaxy. That wasn't always the case. Herschel, the first person to try and map the Milky Way galaxy, came up with this as his model of it. He did this just by looking in various directions and counting how many stars he could see, and thinking that if he could see more stars, then it probably extended further in that direction, which was an eminently sensible idea, but didn't take account of things that we now know, things like dust and obscuration that block you from seeing certain things. So anyway, our Milky Way looks much like this. We have the center in it, and we're out here on this yellow bit here, which is where the sun is, which is about halfway out, somewhere like that. And most of the visible stars in the night that you can see with your naked eye are somewhere in that yellow circle. So there's a lot more to the galaxy than we actually can see there. Now, the next unit of dimensions is the width of the galaxy, and it's about 100,000 light years. So that does give you a sort of sense of the size of how big a galaxy is. So if you could travel at the speed of light, which we can't, but suppose you could, it would take you 100,000 years to get from one side to the other. And light is about the fastest speed you can go that's allowed by the universe. So 100,000 light years, or 30 kiloparsecs. So kiloparsecs being 1,000 parsecs. Once you're talking kiloparsecs or tens of kiloparsecs, you're talking on sort of galactic scales. So when we throw around kiloparsecs, you can think fractions of a galaxy or bits of a galaxy, that sort of thing. The next unit up from that, which is the megaparsec, is the distance between galaxies. Typically, they don't all fit to a grid, but if you travel about a megaparsec, you go from one galaxy to another, or you do if you're going in the right direction. They're that sort of distance apart. And if you go up again to the gigaparsec, or a billion parsecs, now you're starting to get to the size of the visible universe. I think it's about 14 or 15 gigaparsecs across, something like that. So that's just an indication. If you're talking parsecs, it's stars; kiloparsecs, it's galaxies; and megaparsecs, it's the space between galaxies. Now, we didn't always know that galaxies were things out on their own. This is the Perseus cluster of galaxies that you may or may not have seen. All these orange fuzzy things are galaxies, and they're just scattered amongst the stars. You can see these white blobs are all stars from the Milky Way, and it's very difficult to tell without measuring distances. Are they just something in the background, or maybe even in the foreground? And they're just part of the galaxy, because there's lots of fuzzy blobs around in the galaxy. Orion Nebula and the Ring Nebula and things like that. They're all fuzzy blobs that are floating around within the night sky, and those are actually part of our galaxy. But these are probably not. Well, we'll give the game away, and I'm sure you all know that they definitely are not. This is the Fornax cluster, one that's been studied quite heavily because it's reasonably nearby, another big cluster of galaxies. And it was actually Hubble who actually made the breakthrough by measuring the distance to the nearest galaxy and working out that it was way, way beyond the furthest stars in the Milky Way. So it was clear that there were lots of galaxies, much like our own, floating around. And this was about the 1930s that he did that. So having worked out that these things are sort of independent bodies, perhaps much like our own, what can you do with that? What sort of science can you do? And often in science, you start by, well, as Alex Rutherford says here, you start by stamp collecting. So he said all science is either physics or stamp collecting, although he did win the Nobel Prize for chemistry. But this is what he did, and what we still do in some sense to make sense of anything that's unknown. you start making collections. So if you're a biologist, you made connections like this. You said, well, all things with 6 legs were insects, things with 8 legs are spiders, warm, fuzzy, cuddly things are probably mammals, reptiles, birds, etc. And you, for any new thing you find, you put it into one of these things, one of these categories, a bit like putting stamps into a stamp album, if you remembered doing that. So, and then from that, you get this idea, and you sometimes get species, in this case, that's sort of very close to being somewhere between a reptile and a mammal, and you learn new things by linking them together. So that's what they kind of did with galaxies. Here's a big collection of galaxies. Can we make sense of that and order them? And yes, indeed we can. This is what Hubble did. He made an ordering of galaxies, a selection of them, and he put them into 4 piles, basically. So much simpler than animals. We've got down here, these are the spiral galaxies, much like our Milky Way. These are the elliptical galaxies. And these two make by far the majority of all galaxies in the universe. Then we have lenticular galaxies. And being a good scientist, he had a kind of bucket for anything that didn't fit, and these are the irregular galaxies. So anything that isn't one of the above 3 goes into the irregulars. And that's a scheme that worked very well. It still works today, although people are starting to suggest other ways to organize galaxies that might be better. And he came up with this. This is his famous tuning fork diagram that we still have to teach our undergraduates, and they all have to learn and regurgitate in the exam, or at least make use of. So we have the ellipticals along here. Here's the ellipticals, and you can see they actually have a number after them. So there's an E0, that's nearly a spherical elliptical galaxy, and an E7 is a very stretched out, or in true naming style, it really is an elliptical galaxy there. So these are kind of like footballs, and these are more like rugby balls. Then we have the spirals, and he broke those into 2 groups, those with bars, bar features like these, and those without bars. So an S with a capital B is a barred galaxy, and an S without a capital B is a galaxy without a bar. And the letter after that, A, B, or C, in lowercase, just says how tightly wound the spiral is. They get looser and looser, and there is actually an SD for very loosely bound things. Then sitting in the middle is the lenticular galaxy, which I'll come back and explain, because it's much easier to explain later. And the irregulars aren't on here, but irregulars are anything that isn't one of these. So with that, let's have a look at some galaxies. So this is, first one is our nearest galaxy. This is the Andromeda one, 2 million light years away, visible allegedly with the naked eye. I've never managed it with the naked eye, I have to say. I've done it with binoculars, small telescopes, and it is rather a fuzzy thing to see. I'm sure quite a number of you have seen it. But in the naked eye, you really don't see all of this. You only see the very core of it. But it is quite large. You can see here it is next to the full moon, so it's bigger across than the full moon. But you really need photographic equipment, CCDs, really, to see the full aspect of it, because that's really what you normally see from the Andromeda, just the very, very core of it, and you can't see any of the other bits and pieces of it, because they just don't pick up in even the largest telescope. So that's Andromeda. That's the nearest galaxy to us, and part of a twin. We think Andromeda is probably slightly bigger than the Milky Way. Sometimes it is, sometimes it isn't. It depends who did the last measurement and what insight they've had. But some other galaxies, here's a Sombrero galaxy. So this is a galaxy with edge on to us. So we can see that it is really quite thin as far as the structure goes. And there isn't an awful lot to see other than that, although you can see a lot of dust along here. This is this black stuff here, which isn't really like household dust. It's more like soot or smoke. It's sort of fine particles of carbon that are floating around, soaking up the light. This is a barred spiral, so you can clearly see this large barred structure that goes across the middle, and then the spiral arms coming out along here. One other feature that's perhaps a little more obvious in this is that there is a colour change. So it's kind of reddish in the centre and bluish towards the outside. And that's actually an important distinction that helps us understand what's going on in the galaxy when we come to look at the science. This is a good analogy for a galaxy. It's a fried egg. There's a sort of a bulbous bit in the centre, which is the yolk, or two fried eggs back to back, I guess. And the very thin white part, that's actually where we live. We live somewhere out here on the white bit. Or another analogy is a compact disc or a DVD, if you've got those. They are about the same relative dimensions, so you can see how very thin the galaxy is compared to its width. So you know, there isn't a lot of up and down movement, but there's lots of move side to side. And if you talk about the galaxy, these are the structures that we usually mention. So there's the bulge in the center, which is the sort of yolky bit, the disk, which is this very thin category. Then there's a vague halo of stars, globular clusters and other things that are sort of loosely attached to the galaxy. They all float around within this halo bit, very much less dense than the rest of it. And then finally, we actually sit, we believe, inside a dark matter halo. So there is this mysterious stuff called dark matter, which we don't really know what it is, but we have quite a lot of evidence that there is something like that around. And it's about 10 times the width of the galaxy. So it's quite a lot bigger than the galaxy itself. And that's what it sits within. So going back to pretty pictures, here's M821, another close by galaxy. M for Messier, as he made the catalogue of interesting things in the night sky that weren't comets. So anything with an M number is usually fairly close. This is another one that this works actually quite well after Christmas. You can usually have enough galaxy chocolates floating around to make your own spiral galaxy. This is a much more, I don't know, sort of outrageous spiral with many arms, often called flocculent spirals that have lots and lots of arms. Again, you can see sort of, although this one is somewhat enhanced by the way it's taken, you can see the sort of red stuff in the middle and the blue stuff on the outside. So it's now come time to sort of explain what's going on there. What do we understand by this blue and the red? And we need a small diversion into stellar lifetimes and how stars evolve. So if we take a basic star such as our sun, it kind of looks a bit yellowish or whitish. And that's really a function of how hot it is. So it's about 6,000 degrees on the surface, and it weighs 1 solar mass, because that's how we work. We say the sun weighs 1 solar mass, and we compare all other stars to the sun, because it's a sort of handy thing. So that's a star like our own, the sun. We can get smaller ones than that. Red dwarfs, you may well have heard of. They're about half to a tenth of the solar mass, something like that. But they don't burn nearly as hot as the sun. They burn at about 3,500 degrees on their surface. So they look predominantly red. So they're giving out most of their light in the red and very little elsewhere. And then we can get much bigger stars than our own, things like Rigel, or much bigger ones called blue giants. They might be 30 times the mass of the sun, and they burn a lot hotter. So this one is 30,000 degrees on its surface. So this is putting out lots and lots of light, but as you go up in temperature, you put out more towards the blue end of the spectrum. So it's putting out quite a lot of red light, but it's putting out even more blue light. So these things look very blue. If you've looked at Rigel, you may well notice that. So these things give their different colours to the different parts of the sky. Now, we don't get many blue giants. They're sort of few and far between. We get mostly red dwarfs, and from sort of red dwarfs up to the size of the sun is the general population of stars. So you sort of get maybe 90% of those to 10% of these, or something like that, or maybe 95 to 5%. So you don't see very many of these blue giants, but the ones you do see are so bright that they just outshine everything else. So you only need a few blue giants to see a lot of the light from that. Now, the other thing to understand about them is their lifetimes. The sun lasts about 10 billion years, or 10 gigayears, and we're about halfway through. A red dwarf burns very, very slowly. It's kind of like almost a charcoal smouldering fire, and they last for 100 gigayears. So far, far longer than the age of the universe. The age of the universe is about here on this diagram. So you can see there's enough time for the sun to be born and die within the age of the universe, but not for a red dwarf. Red dwarfs will go on for many times that. Blue giants, on the other hand, because they burn so rapidly and so voraciously, they go through their fuel very quickly and in just millions of years rather than billions. So a blue giant like this might burn through its fuel in about 15, 20 million years, which obviously sounds like a long time, but it's actually peanuts in astronomical terms. The dinosaurs lived 65 million years ago, so there's enough time for 2 or 3 of these blue giants to be born, live and die in that time. So if you're going to have a planet that you wanted to evolve life on, probably a blue giant would be a very bad choice, because it would hardly have time to get going before it would sort of explode, and blue giants do explode quite dramatically. So this tells us now what's going on in the galaxy, because this is all blue along here. This must be full of blue giants. I mean, it's full of lots of other stars as well, but the blue giants are outshining it. And in the center here, it's red, so that's mostly stars like the sun and the red dwarfs that are sitting around there. So what does this tell us? Well, this galaxy is many millions of years old. So, and these blue stars only last for a few million years. So they must be turning over quite a number of these. There must be lots and lots of these blue giants being formed and being born all the time. And this turns out to be the case. And in the Milky Way, for instance, there is about, on average, 1 new star born every year. They take actually millions of years to actually form and light up, but on average, that's about the cadence of it. That every year there's about a new star added to the Milky Way. There's also a few that probably 1 or 2 that die as well, but there's this turnover of stars, and we can see it's mostly taking place in the spiral arms. There's not very much going on in the center. This is looking very red. So there's not many blue stars being formed there, and the red stars just keep on trucking because they last for so long. Here's another nice one with lots of blue stars in the spiral arms, and again red towards the center. And one other feature of spiral galaxies is the stars are all pretty well ordered. They're all going around by and large in the same direction. There's a few odd ones here and there that buck the trend. But by and large, nearly every star goes around in the same direction. So we can actually measure how quickly stars rotate around the center. We can plot curves of that. We can do all sorts of things because they're nicely ordered, and they are amenable to this sort of analysis. And it takes about 250 million years to go once around the Milky Way from where we are. So, we'll be back here again in 250 million years, at which point, hopefully coronavirus will be over and done with. So that's kind of a quick whistle-stop tour through spiral galaxies. Now, the other major one is these elliptical galaxies, and these are much less interesting to look at. They really are just fuzzy blobs. They're brighter in the center, less bright towards the outside, but there isn't a lot else you can see about them. But 2 other facts that you should be aware of. Firstly, the stars are going sort of haphazardly around. They're all going around the center, but they're not all going around together. They're just going around on their own orbits, whatever they feel like. So we can't say how long it takes to go around elliptical galaxies, because they're all going around in different directions and different rates and all sorts. But this leads to the other thing that distinguishes elliptical galaxies. They are really sort of three-dimensional objects. So the spiral galaxy has this bulge in the middle, which is sort of three-dimensional, but the elliptical galaxies are just solidly three-dimensional. They spread out in all directions. So an elliptical galaxy, if you were to actually hold one in your hand, would look much more like a rugby ball. So it would have, you know, 3 dimensions, or a soccer ball if it's an E0. So, you know, they're these fuzzy amorphous things, very little structure. And here's an E5, so a slightly stretched one. The other thing you can probably see is that the color is very much red. So they don't really have any new stars forming. They are, we call them red and dead in the business, I guess, because they're not making any new stars. So they give off mostly red light, because they're just things like red dwarfs and our suns that are just coasting along for the next 100 billion years or so. So, you know, they've got lots of life left in them, but they're not really very active places anymore. So they just sort of coast along. This is an E0, M89, a very circular one. And this is an E7. That's about as stretched as you can get. Theoretically, you could get to an E8 and an E9, but they tend to fragment into 2 galaxies at that point. They get too stretched. So that's elliptical galaxies. Those are that, and the spiral galaxies are, you know, account for a large fraction of all the galaxies in the universe. Oh. The other ones that I did mention were the lenticular galaxies, or S0s. And these are a bit easier to understand now, because these are basically spiral galaxies in which you can't see any spiral structure. So you can't see any spiral arms, but they are quite flat. They are like the 2 fried eggs back to back, but you can't see any spiral structure. They're also very red, so they're also not making stars. So these are kind of like spiral galaxies that have run out of fuel. They haven't got enough fuel left to make any new stars. So they're just sort of coasting along and mostly undisturbed. Then we have irregulars. So this is M82. This does look a little more like a galaxy to the naked eye, but with this one, with the infrared, you can see these huge outflows. So it doesn't look like an elliptical. It doesn't look like a spiral or a lenticular. So it must be an irregular. And in this case, you can also see lots and lots of blue. So this is also characterized as a starburst galaxy. So this one is making lots and lots of new stars. Maybe hundreds of stars a year are being made in this one. And it's really a brief burst of enthusiasm. Something has stirred everything up, and it's gone crazy making new stars. But it come back in about a gigayear. This will probably have settled down to something red and dead at that point. So we sort of caught this one in the act. Then we have other ones like this dwarf irregular. This is just a small irregular galaxy. You often find these around bigger galaxies. So we have at least 2 obvious ones around the Milky Way, the small and large Magellanic Clouds. They're also characterized as irregular galaxies. And that's largely because they're being harassed by the Milky Way. The Milky Way has a huge amount of gravity. And whenever these things try and settle down into becoming something more stable, the Milky Way gives them a tug and rips stars out of them and so on. And it will eventually devour them, and they will be gone. But we've got about 1 billion years left before the Milky Way eats these up. And there's quite a few other dwarf galaxies around, but none as prominent as these 2. So we thought we'd classified galaxies, we got everything sorted out, we knew there were sort of 4 main types of galaxy, and we were kind of done. And then, you know, as happens, nature throws you a small curveball, and we came across a new type of galaxy. Well, it wasn't really a new type, it was an existing type like this one. This is a spiral galaxy. But this was Carl Seifert, an American astronomer, looking at these things and said, I've just looked at this particular one, M106, and it has a very, very bright center. And that's something astronomers do a lot of, is measure how quickly the light changes across galaxy to try and classify them. He said, this is much brighter than all the other galaxies I've looked at compared to the rest of it. So there's something funny going on there. It's kind of active, it's doing something. I'm not sure what it's doing, but anyway, he found a few more of these, published a paper, and they've been called Seifert galaxies ever since, after Carl Seifert. So he discovered those in about 1940s. And since then, we've discovered quite a few more of these things called active galaxies. In fact, there's now a whole host of them. So there's Seifert, and soon they found there are actually two types of Seifert, Seifert type 1 and Seifert type 2. And some people even go as far as to find a Seifert type 1.5. So there's that. Then as we investigated further, we found that there are these, this one here is also an active galaxy because something funny is going on in the center. But if you overlay, as we got better telescopes and more wavebands, if you overlay the radio spectrum on top of this visible spectrum, you see exactly what this thing is doing. It's a very, very active galaxy. It's shooting out huge clouds of material out into intergalactic space, and has been doing for a really long time. You know, if you think back, it was 100,000 light years to get from one side of the galaxy to the other at the speed of light. This is an elliptical galaxy, and they tend to be bigger in general than spiral galaxies. So if this was 100,000 light years, you know, this is much, much further to go all the way out here. So this thing has been shooting stuff out of the galaxy against the combined gravity of billions of stars. There's at least 400 billion stars in the average galaxy, maybe more in an elliptical one. So there's a lot of gravity there to pull stuff back, but this is being shot out at the escape velocity of the galaxy, which is quite considerable, and has been doing it for many, many years, millions and billions of years, probably in this case. And it's certainly not the only one. So here's another one, another radio galaxy, also shooting stuff out of the center. So there's quite a few of these things called active galaxies. And then we discovered these things called quasars, originally thought to be stars because they seem very point-like, but it turns out they're actually galaxies, and you can see them a long way across the universe. In fact, we use them as sort of lighthouse beacons almost to do signs on the intervening medium between the quasar and ourselves. But you can see from this one that's been diddled with a bit, this is a Hubble Space Telescope of a quasar, but they blocked out the quasar bit of it, and you can see the sort of ghostly galaxy behind it. So quasars are actually galaxies. They just look like stars because they're so bright. You can't see the rest of the galaxy in comparison. Then there's a whole heap of these things that I shan't bore you with, but here's another one, a blazar or a BL-lac. Once upon a time, I did know the difference between a blazar and a BL-lac, but it's a very fine distinction, and there won't be a test at the end. So we seem to have all these active galaxies, we seem to have like just you know, more and more of these things, and they all seem to be without end almost. But it turns out they all have they're all really basically different forms of the same thing. So you may know that at the center of every galaxy that we've looked at in enough detail, there is a supermassive black hole. So these are things that are millions to billions of solar masses. So you know, you need 1 million suns or 1 billion suns to form some of these things. So they're extremely gravitationally strong, and they would suck in quite a lot of material. But as the material comes closer and closer, it gets faster and faster. A bit like water going down a plug hole, it gets faster and faster. And actually, before it falls into the black hole, sometimes you get these jets occurring where the material is ejected out and stuff goes shooting out. Meanwhile, all this stuff around, circling around, is getting hotter and hotter and glowing in all sorts of exotic variations. Of course, we have seen one now. This is a picture of a black hole taken by the Event Horizon Telescope. But anyway, this seems to be what's going on. You have this black hole right at the very center with this cloud of pink material here. It's not actually pink, but that's what it is in this picture. And sometimes they have a jet and sometimes they don't. And then really it's just which way you're viewing it on the sky. So if you're looking straight down the beam of this jet, then you're seeing one of these blazars or BL-lacs. If you're looking slightly off to the side, then it looks more like a quasar because you're seeing quite a bit of the beam, but not sort of full in the face. You can see these other things here. These are all radio galaxies. This is a Seyfert type 1. Looking into it, you also have this orange torus of material that's not going round quite as much, but it obscures the black hole. So if you're a Seyfert type 2, you're looking in this direction and you can't actually see into where the black hole would be, but with the Seyfert you can, Seyfert type 1 you can. So that's really kind of the distinction. I guess Seyfert 1.5 is about this angle here. So actually they're a lot simpler than you might think. They're all the same mechanism. Often early on they had this jet associated with them, and then that tends to switch off after a few million years, and they get to just one without a jet, but is still highly detectable. And then in the case of the Milky Way, they go quiescent and they don't feed anymore, so you don't get any of this sort of activity going on unless something comes too close to them and they start to smack on it. So that's active galaxies. They're all just classes of the same thing, really. Then we can find out that the universe isn't static. If we could wait around for a few million years, you can actually see some galaxies do collide with one another. Galaxies often form a bit like stars in groups or clusters. So sometimes you can get 10 or 20 galaxies in a group, or in some places you can get many hundreds or thousands of galaxies in some cases, all in a big cluster, we call that. And when you get them all grouped together that closely, sometimes they kind of fall out and attack one another. So here are two galaxies that are just starting to attack each other. And if we come back in about 1 billion years, we could see what would happen. But unfortunately, even our PhD students won't sit around for 1 billion years to watch that. They insist on some quicker activity. But you can look around the sky and you can catch them sort of in the act. So here's the antenna galaxy. So here's the original galaxy, and here's a colliding one much further in. And you can see there's a lot of star formation going on here, lots of blue colors as all the gas and stuff gets stirred up and forms new stars from this collision. But come back in 1 billion years and there probably won't be nearly as much to see. Then there's a whole load of oddities which I've just thrown in just for fun. The largest galaxy, which is not this is a spiral for scale. If we shrink it down to about this size, this is the largest galaxy with the catchy name of IC 1101. So that's a very big galaxy and an elliptical galaxy, as elliptical galaxies are often much bigger than spiral galaxies. This one's a sort of Darth Vader galaxy. You can sort of see Darth Vader's spaceship there. So looks a bit like that, found in the infrared. And to go with that, here's the lightsaber galaxy out distant space. Unfortunately, it doesn't look like this in visible light. This is an infrared light picture. This is the very furthest galaxy we've seen, GNZ11, which is 13.4 billion light years away. The edge of the universe is notionally 13.8 billion light years, so this is almost as far as you can get. This is a ring galaxy. There aren't very many of these, which is just as well because we don't really know how they're made. We suspect it's an interaction with some other galaxy. Some people have done some work on that to try and work out how it happens, but as there are very few of these around, not a lot of time's been spent on that. Something you may heard of is the BCG, which sounds like a Roald Dahl type thing, but it's the brightest cluster galaxy. So I said you get these big clusters of galaxies, and they usually have a very bright central galaxy, which is in this case an elliptical galaxy, and they sort of eat some of these other galaxies slowly over time that are circling them, so they grow bigger and bigger. And then perhaps one of my favorite acronyms or names is the LERG, ULERG and ELERG. I just find it quite a fun word to conjure with. So I usually challenge people at this point to try and drop it into the conversation. You know, have you seen a LERG? Do you know what a LERG is? Are you cognizant of ULERGs and ELERGs? So a LERG is a luminous infrared galaxy. So that kind of gives away all the other ones as well. So this is a galaxy that doesn't look anything special in optical light. In fact, they look fairly dim, but if you look at them through an infrared telescope, then they light up very, very brightly. So there was a whole class of these found. So they obviously had to think of an acronym, and somebody not very adventurous came up with luminous infrared galaxy. So that's what we have here. And then they found some more that were much brighter than that. So we have the ultra luminous infrared galaxy, and then the inevitable happened, and they found another class of these that were even brighter than ULERGs. So we have the extremely luminous infrared galaxy, and luckily we haven't found any brighter than that, because we are struggling for adjectives at that point. So a LERG or an ELERG or a ULERG, they're all sort of the same thing. They're galaxies that have generated a lot of this dust stuff. So this sort of sooty smoke, and they've generated a lot of it from the stars. Most stars generate it, but these seem to take it to extremes. So they've got a lot of this soot stuff floating around in the galaxy, and that obscures a lot of the light. So so a lot of the light from the galaxy doesn't really escape. It just gets blocked out by the soot. But you can't destroy energy, so the soot sort of soaks up the light and slowly gets warmer and warmer, and then starts to radiate it away as infrared light. So these are things that are sort of shielded by a cloak of dust, but you can't hide forever, because they still give it off in the infrared. So that's why they sort of stand out in infrared. Then if we really want to look at things and see how they evolve, about the only tool left in the box is simulations, which is kind of where I got started. So, you know, about half the astronomers in our department go off to telescopes like this to do their work. Others do this sort of thing. They mess around with maths, and we share a department with particle physics group. So they look at more cosmological things, dark matter, dark energy, and so on. But I just throw up here one of their seminars that they have every Friday. And if anybody can make any sense of that, they will be doing much better than I have. So I've learned really not to go to their seminars unless I can actually make sense of the title and the abstract, because I've learned from bitter experience it never gets any better. They just go into a more and more obscure mathematics. So anyway, we don't do that. What we do is we play with computers, and we make big simulations of the universe, how it all fits together, how galaxies form, and so on, because you can watch them form in front of your very eyes. It uses a very simple formula, which is Newton's law of gravity. It's very straightforward to solve. We're helped a lot by the fact that the universe is made of this sort of mixture. So this yellowy stuff is what we know. That's atoms that make up the Earth and the Sun and all the visible stuff. The dark matter is the stuff we can't see, but has a lot to do with gravity. And dark energy is stuff we really don't know what it is. But luckily, it doesn't affect things. But you can do a very good simulation with dark matter because it's very easy to work with. So because it doesn't have a lot of the properties that regular matter does, so it's really very, very simple to work with. And we try and reproduce things like this. This is a map of the universe done by telescopes. And so we're sitting right at the center here on Earth, and every dot here is a galaxy in the universe. So wherever they find a dot, they put, wherever they find a galaxy, they put a dot, and then sort of make up a scatter plot of galaxies. And it was done initially to see, how are galaxies distributed? Is there like a grid of them? Is there one every megaparsec, or do they cluster together, or is there some structure to them? And you can see there is some structure. There are these big collections of galaxies. There's also these places where there don't seem to be very many galaxies at all. So this is what we have to aim at in our simulation, and we can indeed do that. Here's a simulation that I ran. So it's starting soon after the Big Bang, and so this one up here is in 3 dimensions. This one is a 2-dimensional view, and you can see the stuff sort of migrates together and gets these sort of tendrils. It's called the cosmic web because it sort of reminds people of spider webs. And these parts here, these sort of yellowy knots in it, are where there's these big clusters of galaxies, where you might get thousands of galaxies, and these big empty spaces are where there's very few or almost no galaxies. So if we look at just to zoom in from one of these simulations, so you can see that here's the big cluster of galaxies, lots and lots of galaxies collected together there, all circling their BCG. There's another smaller cluster here. We would be somewhere off here out in the backwaters because there's not very many galaxies near us. But we can compare it to reality and say, how well is the simulation doing? Does it actually match what we see? It's not going to match it identically because we don't know the precise starting conditions of the universe. But yes, it does. And here's a map done. So the stuff in red is a simulation run on a very large computer, run several years ago now. And the stuff in blue is observational data. And you can see these sort of walls of galaxies here. This is the Great Sloan Wall. You can see something similar in the Millennium simulation. You can see these sort of voids here, and there's voids here. And you can apply statistical techniques to say how similar are they, not just by eye, and they turn out to be very similar. So we're doing very good work on this, enough so that we now believe our computer models are sort of telling us at least most of the truth. And then you could look at how galaxies interact. You can put them into computer models. And this is quite a nice one done by Volker Springel, who's an excellent simulator. So he was looking at what would happen if 2 spiral galaxies collide. And this is just looking at the gas. So this is the gas is what makes new stars. So he was looking at these 2 to see what would happen if 2 spiral galaxies collide. And the color is basically how hot that gas is. So red is hot, blue is cold. So they collided together there. You can see the gas is all stretched out. So he didn't show any stars in this case. So you can see there we've had a burst of star formation probably at this point, and then soon following that you get supernova explosions as stars go pop. And part of the explosion is they blow a lot of the gas out of the galaxy. We also get the supermassive black holes combining, and they often form these sort of jet-like structures and shoot even more stuff out of the galaxy. So here we can see explosion after explosion, and all that gas, or most of the gas that was in that galaxy, seems to have got blown away. And what little is left is now very, very hot. And you need very cold gas to form stars. So this is quite some possibility that this is what is happening in these elliptical galaxies, that they may well be formed from spiral galaxies colliding, because they end up with a very mixed set of stars and very little gas, and what gas there is far too hot to form stars. Same thing is going to happen in our backyard. You may well have seen this simulation. It's been around for a while, done by some people at NASA this time. This is our backyard. So this is the Milky Way galaxy sitting around. I said we're in a very unpopulous part of the galaxy. So there's really only 2 large galaxies, ourselves and Andromeda, and then this smaller Triangulum galaxy, which is some way to being a dwarf galaxy. But at about 4 billion years, you probably know that Andromeda is on a collision course with the Milky Way. So at 4 billion years, there we go. We've smashed into Andromeda, and the Milky Way have collided together. They've thrown out lots of stars. Some of them will be gone forever. but there we are, a few more smashes together, and you will probably lose a lot of the gas, but also the motions of the stars will be highly disrupted, so they will be going around in all sorts of directions at this point. So what started out as two lovely spiral galaxies is now a complete train wreck, and what we'd probably categorize as an elliptical galaxy. This other one, M33 Triangulum Galaxy, that's also for the chop. That will be devoured by this large thing, probably called Milkdrometer at that point. So that's almost all I've got to say on this, except a few things that we've still got left to do. So I thought I'd just throw out a few open questions, things we still don't understand, which is what keeps us in work at Nottingham University and other places looking at galaxies. So firstly, I said pretty much every galaxy we look at has a supermassive black hole, much like this one that's been imaged here. There's certainly a big one at the centre of the Milky Way at about 4 million solar masses. This one weighs about 4 billion solar masses, so it's about 1,000 times bigger. And we really don't know how you make these things. We know how to make a black hole, but only by killing off a star. So if you form a black hole by that process, you end up with one that maybe weighs 10 solar masses, 20, 30, 40 at a stretch maybe. So to get to 1 million, you've got to do quite a lot of work to make it that big. You can add stuff to a black hole. They will certainly gobble up anything that falls within them, but very quickly they will consume what's around them, and then the rest of the stuff tends to orbit at a safe distance. So we really don't know how you make those. And by looking very far away at very distant galaxies, we can see evidence of these huge black holes in very, very early galaxies, just a few, maybe hundreds of million years after the Big Bang. There are these these galaxies that are starting to form, but they already have these supermassive black holes. So that's the secret. If anybody knows how to make a supermassive black hole in short order, that would be very much appreciated. Another thing quite a lot of people are doing at Nottingham is looking at this sort of scenario. So if we look at galaxies in general, we have a blue cloud. These are all the spiral galaxies, and the red sequence, these are the elliptical galaxies. So by and large, they make up most of them. And we think there is a progression that spiral galaxies probably form elliptical galaxies by collision or other processes. But if you look on this thing here, so this is the blue going to the red, but these are quite a lot less massive than these things. So to get from here to here, you've got to put on a lot of weight and go quite red. So sometimes 10 times as much mass is in a red sequence galaxy than in the blue cloud. So is it the case that they get heavier and heavier and then they turn red? Or do they get redder and redder and then get heavier? So, that's one thing we're looking at. And there's this sort of green valley, which is somewhere between red and blue, where if you can catch galaxies in this green valley, they are sort of in transition. So there's been quite a lot of work to try and catch these things and look at their properties and see, what are they doing? Which way are they going? Are they going this way or that way? And to do that, we'll need new tools. So this is Gaia, a satellite that's mapping the Milky Way. So we're getting a very good picture of how our own galaxy works. This is just some animations done by ESA using the Gaia data. So because it's measuring like a billion stars, measuring how fast they're moving and where they are, in this case, they did a quick study and said, well, let's look at all the woes that are moving very fast. So all these stars here with the sort of yellow trails, they're moving faster than the escape velocity of the Milky Way. So these will eventually leave the Milky Way. And these might be stars that have come in from elsewhere and are just passing through. Or another possibility is that they've been given a large amount of energy. They've been in a sort of interaction with 2 or 3 stars, and one of them's come off worst and been kicked out of the galaxy, basically. So Gaia is producing so much data that a lot of people are working on this. It's like saying having a GPS for the galaxy. Another thing we're looking forward to, particularly for very distant galaxies, is the James Webb Space Telescope, due to be launched, fingers crossed, on the 18th of December after many, many delays. As you probably know, it's got to go through a lot of steps to turn into a working model. So there's about 300 critical steps from a folded up nose cone to a working telescope. But already people are desperate for this data. The first run of James Webb Space Telescope is already hugely oversubscribed. They've already allocated all the time for the first year's observation. So yeah, there's just so many things that this could be used for. Another thing that could be used is this huge radio telescope called the Square Kilometre Array. So this is a big array of radio dishes scattered mostly across South Africa and Western Australia, but they're not individual dishes as such. They're actually all connected together, so they give one signal together all at once. So it makes for a radio telescope about the size of Africa sort of thing by the time you add all these things together, because there's a few other dishes dotted here and there to make it even larger. So that's going to give us our next jump in radio telescopes. In visual, we've got this huge monster that is about half built now. This is the ELT, for Extremely Large Telescope in Chile, sitting next to the VLTs, the four VLTs. So these are 8-meter mirrors, and this is a 39-meter mirror, so it's a huge jump in size. Will be sort of one of the wonders of the universe. There it's artist's impression, because they're built up to about this layer, I think, at the moment, the last pictures I saw of it. This is what a 39-meter mirror looks like. So all of those of you with aperture fever and wanting a bigger telescope, this is as big as you can get at the moment. So these are all things that are really going to help us with our next views, because as ever in science, as you get a bigger and better instrument, you get answers to some of the questions you've been asking, but you also get new questions posed because you find things that you didn't realize you didn't understand. So let me conclude with that. Let me say that galaxies are big, about 100 to 400 billion stars, most of those with planets. Lots of room for expansion. There's room for kind of like 10, 20 stars each for every person on the Earth, and the planets that go with it. And if that wasn't enough, there's another 2 trillion galaxies to explore. So lots of room to settle down. Research continues, and I said things like the James Webb and the ELT will help us push back the frontiers and discover new things. So we're very much looking forward to that. And so with that, let me wrap up and say thank you very much for your attention, and thank you for listening. And if you've got any questions that I can answer, I'll be willing to have a go. Thank you.
Well, thank you, Julian. That was fantastic, as ever. Absolutely fascinating. Everybody can unmute if they want, and put your cameras back on as well if you wish. And the floor is open to questions. Who would like to ask the first question? Or, well, actually, I think, Mark, would you like to just give us the traditional thank you?
Well, I was going to at the end, actually, but yeah. I was going to actually ask Julian, your PhD students, do they ever do any visual observations, or is it all theoretical?
It's less and less, I have to say. They do still get to go to telescopes. We've got one of our PhDs actually got a year's secondment to, which one it is? One on Canary Islands. So she will be operating that telescope for sort of the next year, working with that. But these really big telescopes, and particularly the Hubble, you can't go to the Hubble and do any viewing, and they sort of discouraged. Well, not discouraged, but it's quite expensive to go to fly across to Peru Chile or Hawaii to visit some of these telescopes. And when you get there, you're not allowed to typically play with the telescope because they are very big and expensive, and the technicians there know what you can safely do with them and what you can't. So occasionally they do get trips to them. There are smaller telescopes where you can actually run them, sort of a ½ meter, 1 meter, 2 meter class telescopes. But the really big ones, yeah, they don't let you play around with that because they are very expensive if you break them.
Because I know you can buy time on some of these telescopes. I think Liverpool University have got John Moore's. You can actually buy time on to it. So, yeah. so I assume your university does that, does it? You know, buy time?
Not usually. We are part of the European Southern Observatory, which runs the VLTs and the ELTs and a few others. And in the case of the Hubble, actually anybody can apply for time on that. It's free. It's just very difficult because to get time on the Hubble, you have to put in a case and say, I want to use this amount of time on the Hubble to study this effect. This is what I'm going to produce from it. This is the science I'm going to produce. This is why I think it's going to work. This is why I can't use another telescope that might be freer, and why I definitely need the Hubble. So you put in that application to use it, and lots of other astronomers also put in applications, and the ratio is about 1 to 10. So for every 10 applications they put in, 1 will get accepted for the Hubble. Things like the VLTs, I think it's nearer to sort of 4 to 1. So, you know, the odds are still against you, but you've got a better chance on that. And then as you go further down, mirror sizes and so on, you get a better chance. But you find a lot of the science has already been done with that sort of classic telescope. So, yeah.
I was interested in some of the objects you were showing up, and I noticed that you showed the Quasar 3C273, which is just about the brightest quasar that you can see with a backyard telescope. Yep. So us poor amateur astronomers go hunting for these faintish quasars, and I was pleased to actually see 37273.
Oh, well done.
And,
fantastic.
And last weekend I was given access to a 16-inch telescope, and we were looking at M33. It was at a dark site, and we were looking at the area NGC 604, which is that area which is like the Orion Nebula, but about 30 times bigger than the Orion Nebula. And it was quite clear in this 16-inch telescope. So did that sort of students ever do that sort of thing, or?
Not really, no. Most of them, yeah, most of the nearby stuff has sort of been done. There are big surveys done of things like Andromeda, but they take you know, very tiny chunks of it and stitch it together, much like making a mosaic. But with things like the Hubble and other large telescopes. So when you get to that sort of detail, you can find new things. But to get that sort of time to map Andromeda in that sort of detail, you need to make a very big case. And usually to make a good case for using that amount of time, you have to collaborate with lots and lots of other people, such that, you know, there's the weight of authorship or something to, and, you know, you say, well, if we get this data, we'll do this with it, with this, this, you know, we have 5 groups ready to use the data. So it's a good case to approve. So yeah, individual students, not usually. What they do, I mean, often in their first year of the PhD, they will just, you know, find some interesting thing to, by going through older data or survey data. There's a lot of survey telescopes that just collect data. Basically, they don't go looking for anything specific. They just collect lots and lots of data. And then you can trawl through that and look for various interesting things. And sometimes they will find something that they can't quite explain, as shown up at sort of low resolution, and then they will apply for time on one of these big telescopes to actually say, right, we found something interesting. Nobody else has looked at it in this detail. we'd like to look at it, and they would get time. And sometimes they also get to visit the telescope. We had one about 4 years ago who, I think she managed about 7 or 8 trips to telescopes during her 3.5-year PhD. So it can be done, but it's getting less and less common.
Without hogging it, just an observation from the very start, where you referred to the Andromeda Galaxy, and I mentioned that we had a new observing site coming up. Well, Chris and I actually went to this observing site last week, and I could see the Andromeda Galaxy naked eye.
Oh, well,
just as I mentioned that.
I think you should definitely mention that. That's definitely one up on me.
Well, it's a bit embarrassing because Mark's a couple of years older than me and I couldn't see it. So, but I was probably looking in the wrong direction. But no, I'm with you there, Julian. I did see it. Actually, that's not true. I went for the USA solar eclipse in 2017, and I was in Wyoming and in a campsite, and there were a couple of guys there who, obviously, I mean, most of the people had gone for the eclipse, but obviously many of them were astronomers anyway, and some of them were out the night before or 2 nights earlier. And I think another night as well, we were somewhere in the in Yellowstone National Park, and it was stunning. As you probably know, anyone who's ever seen a really truly dark sky, you can get quite disoriented because there are so many stars, you lose the constellations. But having got my orientation right, yes, I could see Andromeda, but I have to confess I struggled the other night, Mark. I think you've got better eyesight than I have. Either that or you're just lying. Yeah. Anyway, fabulous. Questions, anyone?
I've got one question. You mentioned about the evolution from spiral to elliptical galaxies. Can anything be said about the difference in ages between them as a consequence of that evolution, or is it really only the stars themselves that you can tell the ages of?
You can get a broad picture of the age up to a certain level, and I mean that you can form ellipticals by colliding 2 spirals together, but you can also form them just because they can form just. So it really depends how the gas flows in initially. So if it's sort of flowing in from just one direction, then it tends to sort of flatten out, and that's when you get the elliptical. But if you've got several sources of gas that flow in originally, then you get this just jumble of stuff.
So it's very much dependent on where directions of gas, how it's coming together, that determines what it's going to end up as.
That's it. And you can almost get ellipticals turning into spirals in some cases. You can get this big bulge of that's an elliptical, and then you get this source of gas from somewhere, and it would spiral round and make a disk. I think that probably happened in the Milky Way, because if you go into the really gory details of it, there's actually a thick disk and a thin disk, and they're different populations of stars. Very difficult to split apart without spectroscopy. But I think the thick disk is the older stars, and then the thin disk is newer stars, and that was probably an influx of gas that triggered this. It's sort of called galactic archaeology, was they sort of scrape away and
get your trowel out, and
that's it. Yeah, try and uncover what really happened there.
Thanks.
It's not terribly easy though.
Julian, I've always struggled with this. I mean, irrespective of the morphology of galaxies, their structures, and whether they follow some kind of, almost like a Hertzsprung-Russell sequence. I mean, you seem to be suggesting at one point that, you have the oldest galaxies are amorphous, they don't have shape because that's how they start, and then they maybe angular momentum, they become spirals, and then spirals interact, and then they become ellipticals. I mean, that's possible. I don't know, but you also said the opposite is possible. But if we were just putting all that to one side, the obvious is that every galaxy, by definition, is essentially a very, very large congregation of stars. It's a city of stars.
Yep.
And each of those stars is an aggregation of gas, which is concentrated. And, you know, depending upon the mass, it could be a brown dwarf, a red dwarf, you know, blue giant, red giant, whatever. But they are discrete balls of gas, each of which in their assembly form a galaxy. And then galaxies themselves are discrete. I mean, that we see these filaments that you showed us, these patterns, but that's on a very, very macro scale. Apart from the stars which are ejected for various reasons from galaxies, given that galaxies, you can't have a galaxy before stars. I mean, stars form first, one assumes, and then these stars somehow are attracted together and become galaxies. I mean, or is it on a much more macro scale that we have a gas cloud which starts to coalesce, and within it we get the stars? I'm still not clear why why we don't just have a universe full of stars, not evenly distributed, but why we don't have stars in pockets of gas which aren't big enough to form galaxies, why we don't have rogue stars. And I don't mean the ones that are ejected. Are there stars which exist independently in intergalactic space, or is every star essentially either in a galaxy or has been in a galaxy? Sorry, that's a rather convoluted question, but you see what I'm getting at, is how this aggregation of matter happens, in that ultimately we still get discrete galaxies.
So which came first, the chicken or the egg, or the galaxy or the stars?
Well, I think obviously the stars come before the galaxy. You can't have a galaxy of no stars, but...
Oh, well, actually, that's a very good question, and it's probably, there's at least 2 PhDs probably in that question. But our understanding at the moment is, so it all starts with the Big Bang, and the Big Bang is not completely uniform, so you get some areas in the universe that are dense and some that are less dense. And actually what triggers everything is dark matter. So for various technical reasons, dark matter can get on and organize very much earlier than regular matter. So that tends to attract itself gravitationally to these denser parts. So that sucks in all the sort of dark matter. And I think it's to do with sound waves originally, that you get these sort of nodes where there's a density and then another density, and that's kind of where you get the 1 megaparsec gap between galaxies. So they will suck in everything around them until you get within the gravitational influence of the next group. So the dark matter forms, that sucks in these baryons, the atoms and whatever, and then they start to form stars within this sort of gravitational well that's created by dark matter. And you do get little pockets of dark matter that also clump together. That's very dependent on the properties of dark matter, actually. If it's particularly cold, meaning it doesn't move very quickly, then you tend to get lots of fragmented structures. If it's slightly warmer, then it sort of smooths it out, and you get a big galaxy and then little dwarf galaxies around it. But if it's very cold, you get a big galaxy and many, many dwarf galaxies around it. So that's still somewhat of an ongoing debate. But yeah, essentially, dark matter falls, clumps together. When the Big Bang has finished churning around, the matter then falls into these big gravity wells and starts forming stars after it's cooled. That's my back of the envelope description of what we understand at the moment.
Following on from that, I have a question. Are there lots of dwarf galaxies that have not been discovered? Is there, like, as observation techniques improve, you tend to start seeing things, you know, that you didn't see before because your observation improved? Very much like now brown dwarfs seem to be, you know, outnumber stars, the typical luminous stars. Is there a whole sort of sequence or number of dwarf galaxies that are still to be found, which don't affect the overall picture of the universe, but just give you another view of the population of galaxies?
Yeah, no, that's a really good question. That is, and hints at another argument that's still raging. So we found, or we reckon, there are probably around about 150 dwarf galaxies around the Milky Way. There's the two really obvious ones, and all the rest are either very small or very diffuse. So we've had to find new techniques for actually locating them, so they're you can almost see through. They're collections of stars, but until you work out where they are, they could just be stars or they could be a galaxy. But anyway, we reckon I don't think they've all been discovered, but it's predicted there's about 150 around the Milky Way. We definitely found some, but in some directions it's very difficult to see them because you're looking through the main body of the Milky Way, so it makes it even harder. But this brings up a sort of dichotomy in that when we run simulations of something like the Milky Way, we produce, with our current best ideas around dark matter and regular matter, we produce about 3,000 to 4,000 of these dwarf galaxies. So there's this missing galaxies question that people rage about, and there's all sorts of solutions to it. None of them are definitive at this point. So if you want to get into that debate, there's a few of these sort of light blue touch paper and retire as you watch astronomers rip each other apart about which the correct solution is.
Excellent.
So yeah, a very insightful question there.
Just following up on the dwarf galaxy thing, you mentioned, did you say 150 in our
predicted? Yeah, I think they found sort of
as regards clusters, irrespective of whether they're regular or globular or whatever, I think it's a similar kind of number or something in the halo of the Milky Way that we know of. When does a cluster become a dwarf galaxy? Is there a rule? Is there a numerical kind of distinction, or is it kind of just a spectrum of size? Is there a difference basically between a dwarf galaxy or small dwarf galaxy and a very large cluster in a local galaxy, I mean?
Yes,
within the halo.
There is, and I can't remember offhand what it is, but I think if you plot, that's what astronomers do, plot graphs, but if you plot, I think, luminosity according to mass and certain spectral things, the globular clusters appear on a different sort of, it's a bit like the Hertzsprung-Russell diagram. They appear slightly offset from the regular. You can sort of draw a line through all the elliptical, spiral and so on. They share certain properties all the way down to these dwarf galaxies, but the globular clusters are slightly off that spectrum. There's one or two that are a bit iffy. So Omega Centauri, is that the one I'm thinking of, the southern hemisphere, the very big globular cluster? People are now thinking maybe that's not a globular cluster, that may be a stripped dwarf galaxy. We're just seeing the very center of it, and all the other stuff has been stripped off it. There's still some debate on that, and quite how you form a globular cluster, again, I don't think there's anybody got a very definitive answer to that either. So that's still ongoing discussions. Yeah. Also heard that some of the dwarf galaxies they think now have black holes in the center, which don't seem to be the case for globular clusters. And they also have a reasonable amount of dark matter associated with a dwarf galaxy, and not with a globular cluster. So that it's a fine distinction, but one that people who work in that area keep making.
Yeah, I think they've established that, again, we're pretty much bog standard, the Milky Way, our galaxy, in that I think globular clusters have been identified above and below the galactic plane, well, maybe not below, but on one side of Andromeda as well.
Yes, yeah, they've discovered a lot.
And they think now that every galaxy, just as they have a black hole, a supermassive every galaxy seems to have globular clusters scattered around its halo, and probably dwarf galaxies. And this is again what the whole thing about the accretion of matter. It's such unimaginable scales that it's hardly surprising that locally you get we don't have a universe full of a finite number of galaxies, each of which is identical in size and identically formed and equidistant from the other. It just doesn't work like that. And therefore you have big galaxies, small galaxies, different shaped galaxies, you have dwarf galaxies, and then you have clusters and clusters around galaxies. And it's, you know, it's so heterogeneous because of the nature of gravity and, as you mentioned, dark matter as well, and just in immense distances, incalculable distances.
Definitely, yeah. And it's we keep discovering new oddities. I mean, there's a couple of galaxies discovered, I think, about 2 years ago, which seem to have very little, if probably no, dark matter in them. That caused a big stir for a while, but that's only 2 galaxies out of like 2 trillion. So it's you know, we can probably explain those away reasonably well.
How can we tell whether there is dark matter around a galaxy or not? Is it just by inferring from the sort of what should be there based on the gravity of it, or is there direct evidence?
Yeah, pretty much what you said. So the gravity. So if you watch how the stars move around the galaxy, they're going at a certain speed, and you need a certain force of gravity to keep them from flying off. And nearly every place we've looked, they're going far too fast for the amount of visible matter to hold them in place by about, you know, a factor of 5 or 6. So, you know, it's not just a few stars down the back of the sofa that are missing. It's huge rafts of stars. Yeah. So it's very difficult to explain. Although we'd all be a lot happier if we knew what dark matter was.
James, I have to ask, sorry, Julian, but I've got to ask James a question. James, are you in the TARDIS?
I am indeed in the TARDIS. Yes, I've converted my living room. So.
Oh, very nice too.
Very effective. I love it.
Well, you could answer quite a lot of these questions by just zipping around the universe. And
yes, I'm just going to pull this lever.
Come back with the answer in 5 minutes, James.
Yeah. It's a shame. Yeah. No black hole in that one. What you were talking about.
Back to you, Mark. If anyone else got any more questions, or I'll hand Mark, if you'd like to take back the baton.
Okay, thanks, Chris. Yet again, Julian, that was a really fascinating and enjoyable talk. It's lovely to have you back. And I would ask everybody, can you show your usual appreciation by raising your clapped hand?
Well done. Thank you, Julian. Fantastic.
Really,
Thank you very much for inviting me back. It's very good to see you.
We'd love to see you again.
Oh, I'd love to come back.
Thanks very much. Okay.
Yes, we will. We'll do that.
Right. What I wanted to mention at the very start, I did say about the new observing site that we've got. And now we can actually pick a date. So it was just to say we are going to try and get a date from the 27th of November onwards. So look at your emails. But what I'd like to know is, because I've got 20 of you here, could somebody just stick up a thumb if they fancy coming to one of our observing nights to get a general feel about how many people might turn up. So I'm going to put up my thumb. So I just wondered how many others quite fancy. Oh, right, you got a few.
That's good.
That's good. That's great.
You don't necessarily have to have kit, but it does help. But we're happy to share. We're not going to stop anybody else looking through our scopes, but the more the merrier.
Yeah.
Yeah.
I would say though, Chris, just to something you sent out when you mentioned the new observing site, you did say for those who want to, there are 2 nearby pubs. And when we went to do the observing night, Chris dragged me to the Crown and Anchor at Lugwardine, which was just down the road. And it was very, very pleasant. We had a very nice drink of butty back. So it's got benefits as well as the observing at this dark site. There is local pub that we could go to have a swift half if one wants to join us. Anyhow, it's just to get a general feel of what might come along. And I know there's this worry about telescopes, looking at eyepieces and everything else. But generally, I think we have to start doing some observing again. And as I said, this is a nice site chosen by Chris. It's got a 360-degree horizon, so you can look really quite low down. And as I said, with a bit of luck, we won't get much interference when we're there. So from that point of view, well done, Chris, finding it. And
yeah, the big advantage, it's just for those of you who've not been before, the big advantage against all the other sites we've had, each site has certain pros and cons. You know, in terms of surface, Bartestry has a very solid tarmac surface, very flat, very solid, no pooling if it rains or something like that. And this one's kind of in between, but it trumps everything else simply because we don't have to book it. And what we can do is give a blanket window, as Mark said, you know, after the third quarter or thereabouts, which for the last month or two has been the 27th onwards. We can say, well, somewhere within this window from the 27th to, I don't know, the 2nd of December or 3rd of December, something like that. We're going to have an observing site, we can an observing night, and we can say that 2 or 3 weeks in advance. Well, we can say now, because we know what the moon's going to do. What we don't know is what the clouds are going to do. And as we get closer, we can nail it and say, right, tomorrow night, chaps, that's it. And, you know, that's when we're going to be there. Not just chaps, sorry, ladies as well. But, you know, the advantage is that we can do it at very short notice. And yes, you know, for those who haven't been, we set up about 6:30, 6:45, observe for a couple of hours, 7 till 9. And if you've got a thirst, then there's the Cock of Tupsley or the Crown and Anchor. I'm a bit of a snob, prefer the Crown and Anchor, but I'm open to, as long as it's wet and it's cold and it's beer, I don't mind. So there we are.
One question about the new site. Would it be okay, like, say, if tomorrow night was going to be nice and clear, would there be any objection, say, to me taking my scope down there and using the site?
Yes, there would.
Right.
At the moment, I've negotiated. I mean, not permanently, Jeff, but at the moment, it's for us to use once a month by notification. So when I say we don't have to book, we don't. We choose when we're going to go. He just wants an email by courtesy, out of courtesy, to let him know, because there are people that overlook the site and need to know that we're not some, well, whatever. We're not the let's put it this way, that we're not the where was it, Mark? Aylstone Park? Not Aylstone Park.
it was Aylstone Park, yes.
We're not that lot, if you follow me. So we don't want to be confused with anybody else. So at the moment, we have permission to go once a month, but at any time of our choosing, approximately once every 28 days to coincide with the moon phase. In the longer term, yes, Jeff, I think we will be able to do that. But I'm just, Francis Milsom has asked the same question, coincidentally. So at the moment, I'd rather people didn't just turn up unannounced, because we don't want to blow it with the farmer. So we'll get his confidence. And, you know, perhaps the other side of Christmas into the new year, I'm sure he'll be fine once he sees that we're not causing any problems. And the other thing is, when we do get there, we must park down one side of the road. It's a very wide road, but it is used for tractors and things. And so we'll park parallel to the fence down the side, one after the other, and set up our scopes in between. So that the other side of the road, we don't want to be both sides of the road, is what I'm saying. But we can sort that out the first time we meet, which hopefully will be the end of this month.
Okay.
So not at the moment, Jeff, but I'm sure it'll be fine in the future.
Yeah.
Right.
Okay. Thanks very much.
Okay, well, that was the message I wanted to hand over. So hopefully we will see some of you again towards the end of the month. I can't remember, Chris, actually, who's the speaker next in December.
Well, we have Dr. Altamirano, who probably Julian knows as well, Diego Altamirano at Southampton. Do you know him, Julian?
I think I've heard the name, but I don't
know
them.
And I did send out, there is a sort of a free, is anybody going to attend on this Saturday, actually, on the 13th, starting at, I can't remember, 12. Katrina said yes, she's going So yeah, it's neutrons, Neil and Roz as well. Neutron stars, stellar objects. It's basically a co-hosted, I think, by Bath, Bristol, and Southampton. I can't remember, but Dr. Altamirano is one of the speakers, and if you watch his talk, that is a kind of intro into his talk, which we're having in December on neutron stars. So if anyone wants to attend that, I did send out the invitations to that a while ago, so check your emails. It's all afternoon. You can dip in and out. You don't have to attend the whole thing, of course, but it's this Saturday, the 13th. Am I right? Saturday the 13th? Yes. So there we are.
Okay. Right, so well, thanks everybody again, and specifically thank you, Julian, for that enjoyable talk.
Yeah.
And we look forward to seeing you again. Thanks very much. Okay,
Thank you.
everybody,
Thank you.
we give that a wrap, and we'll see some of you again.
Yeah, I will send out, as I said, thank you, Julian. Bye-bye. I'll send out an email about the observing, or Mark will let you know. We hope to see some of you there. Okay.
Yeah. And
thank you, chaps.
Okay.
Thank you.
Okay, John.
Bye-bye, everybody. Bye-bye.
Bye.
Sue, it's lovely to see you, Sue.
Oh, yeah.
Really lovely to see you.
Yes. Yeah, it's all going quite well. Yeah.
Oh, yes.
Looking forward to it.
Okay.
So I will be there as well on Monday.
Yeah. Oh, yes. I know.
Yeah.
Okay.
Yeah. Okay.
Look
That's
after yourself.
lovely.
We'll have a chat then. Take
We'll
care.
have a longer chat on Monday. Okay,
Yes.
Sue.
Yes.
See you Monday.
Bye, everybody.
Cheers. Bye-bye.
Cheers. Bye.
Bye.